Thank you. Okay, so first of all, thanks for inviting me. This is my first Aegean conference, actually. So we're going to start today talking about variability in Aegean. So we all know that black hole accreting systems are powerful X-ray emitters, but we also know that this X-ray flux is highly variable, and this variability is observed over a large range of timescales. Now, for Aegean, these timescales go from seconds, let's say, up to years. Now, variability is observed in basically any waveband. This is a plot from a Swift observation of NGC 4593. And as you can see, there is variability pretty much in all bands. But what we observe is that the most rapid variations are seen in the X-ray band, because this emission comes from the most compact regions around the black hole. Now, I'm going to focus on X-ray variability, but there will be a bunch of talks later focusing on variability in other wavebands where we see signatures from the jet. Okay, so first of all, why is variability important? I selected a few reasons that, to me, make variability important, and this is also representing the outline of my talk. So first of all, we observe variability around any compact object having an accretion disk, and this is telling us that variability is a fundamental property of the accretion process. So we need to understand variability to fully understand accretion. Then variability does not only produce variations in flux, but it can produce strong variation in spectral shape. So by neglecting this variability, we surely lose much of the information that it conveys. Then variability can be used as a powerful tool. So I will go through some things that we can constrain using variability. And finally, I hope I have time to go to describe some transient phenomenon observed in Aegean. Okay, so first of all, we have to make a distinction here. So we have two kinds of variability. We have stochastic variability and transient events. So stochastic variability refers to the variability that we observe every time we look at an Aegean. So it refers to these random flux variations that are continuously observed in Aegean light curves. While with transient event, we refer to short-lived occasional events. So first of all, do we understand variability? Of course we don't. So the first thing we can do to try and build a model of variability is to characterize it. Now, the first way, let's say the most used way to characterize variability is by building a power spectrum. Basically, a power spectrum shows the distribution of variability power over frequencies, temporal frequencies, which is the inverse of the time scale. This is an example of the power spectrum of two very well-known Aegean. And these are basically the time scales where variability is observed that goes from sub-minutes up to years. Now, the shape of the power spectrum is pretty smooth. We observe more variability at lower frequencies, which means that these objects have more powerful variations on long time scales. And this is what we call red noise. We don't observe features on top of these power spectra, apart from a break or a light or a bending of this spectrum, which we refer to as break frequency. And this should correspond to some fundamental time scales at some characteristic radius of the accretion flow. But since these time scales depend on many unknown parameters of the accretion flow, it is really difficult to directly associate these features here to some specific time scale. And here, just as an example, I show three typical time scales of the accretion flow at 10 RG for a source like NGC 4051, just to compare this frequency break with known time scales. So this is the crossing time at 10 RG, the thermal time scale, and the viscous time scale. So as you see, there is no clear coincidence within the two. Now, one thing that we used to do, since it's not very easy to study variability in Aegean because we cannot cover all the possible time scales, is to draw analogies with black hole binaries. Because black hole binaries varies faster, we can see transitions over human time scales. And what we see in general is a lot of analogy. And this, for example, shows how the high frequency part of the power spectrum in Aegean looks pretty much as the power spectrum seen in the high frequency part of the power spectrum seen in black hole binaries. And this is telling us that probably the variability process is the same in both sources. Another way to characterize variability is to look at correlations between X-ray bands. And so when we do that, what we observe is that we measure time lags. And what we usually observe is that the harder bands are delayed with respect to the soft bands. And this is seen over a broad range of timescales, although the measurements are pretty sparse. Again, we can draw analogies with black hole binaries. These lags are routinely observed in black hole binaries in all states, basically. And as you see, they are pretty similar. Now, the problem with Aegean is that to measure lags well, the easiest way is to have a continuous, uninterrupted light curve, and the length of this light curve determines the lowest frequency that we can sample. So in general, probably the best instruments that we can use are those on board XMM, because it gives a long continuous light curves. But this means that our sensitivity is limited to this range, which would correspond to this range in black hole binaries. So we are missing a lot of information. And these lags are so better studied in binaries. There is only one source where it was possible with some techniques to push this measurement to the lowest possible frequencies, and it seems that these lags behave like they do in black hole binaries. However, all this doesn't tell us much about the variability process. In particular, this is because there are several models that can reproduce this broad range of timescales and this shape of power spectrum once the parameters are adjusted. So we need to find some fundamental property of the variability that allows us to build a model. So one of these is this RMS flux relation that has been found studying both Aegean and black hole binaries. So basically, this relation is telling us that the source is more variable when it's brighter. However, I don't think this is telling much. The best way to see this RMS flux relation is to consider this sort of representation here. So here we see on the lower part of the plot, we see basically the variance, or called in a more fancy way the excess variance or the RMS, measured over a given interval, a given time interval, small time interval. So this shows how the variance of the light curve varies over time. And this shows the average flux over these time intervals. So basically, this samples the variability over the short time scales of the time interval we selected. This is instead following the variability over the longer time scales, so time scales longer than the time bin we selected for this light curve. In other words, this is telling us that the short time scale variability is influenced by the long time scale variability. So there should be some way for the short time scale variability to be modulated by the long time scale variability. And this turns out in this sort of correlation. So they are linear relation between the RMS and the count rate. They are observed in Aegean and in black hole binaries, and there is only one known case of a non-linear relation that is being found in one Aegean. Okay, so let's try to build a model. So as I said, it's much easier to do, well, these models basically has been proposed to explain variability in black hole binaries. So with the limitation, I said we are just extending it to Aegean, but it seems it works pretty well with, for black hole binaries, at least from a qualitatively point of view. So this model is a model of propagating dot fluctuations. Basically, what the model assumes is that perturbations in the mass accretion rate are produced at any radius on a wide range of timescales, but only those timescales that are longer than the diffusion timescale can propagate down and influence the variability produced at smaller radii. So basically, this model can produce this sort of Lightcurves where we observe variability over over different timescales. And this model works pretty well for to reproduce the power spectrum shaped, all the variability timescales that we observe, the RMS flux relation, and these hard X-ray legs. Now, whether or not this is physical or not, well, it's something that is being tested, looking at like with numerical models. Basically, what is being there are many groups that are trying to test this model using GRMHD simulations, where basically a torus or a disk threaded with a magnetic field and subject to magnetorotational instability is let evolved. And what is observed is that actually these perturbations are produced and can be diffused down. And they produce all these kind of observables that we see. Okay, so the next point is whether or not we can discard variability, because sometimes we are faced with the problem of having not enough counts. So the best thing to analyze our data would be to average over long time scales, and this would, this might be a problem if the object is variable. So of course, whether or not we can discard variability depends on the time scales that we are sampling, so that we need to sample. For example, this case shows how variable absorption can imprint strong spectral variations in Aegean, and this can occur in this case on timescales of months to years, but it has been shown that the variability in absorbers can be observed also on smaller timescales. But we can also see variability intrinsic to the X-ray corona, and in this case, the timescales for spectral variations are much shorter. So it depends. So it depends on the case. However, why should we neglect variability? Variability can be used as a tool to study these objects. And so let's go through some applications. So one of these applications is to use variability to constrain the geometry of the accretion flow. So this is because this is doable, because since the primary emission is variable, all the time the variable emission is reprocessed in a medium, then the reprocessed emission will be variable as well on some time scales. And what we will see is that the reprocessed emission would have a time delay imprinting on it because of the separation between these regions. Now, this is what is routinely used to measure the black hole mass in optical UV reverberation techniques, but this has been possible to do also in the X-ray band, where X-ray reverberation lags have been finally found. So in the X-ray band, these reprocessed emission delays, X-ray reverberation lags, are seen in the highest frequency sampled, and are seen as negative delays, negative lags in these plots. In in this case, the component that is responding to primary continuum variation is the soft excess, and it is doing that with a time delay of about 20 seconds. This kind of lags have been seen in several sources, in several Aegean. So this is a plot that shows the time lags as a function of black hole mass for a sample of non-jetted unobscured Aegean. And what we see here is that these time delays all mark very short distances, which is telling us that the corona should be compact and the inner disk should probably extend down to the innermost stable circular orbit. And this kind of lags have been measured also in the iron K band. Next, we can use the same technique to measure changes in the geometry. So if we are looking at the same source and we see changes in the amplitude of the reverberation lag, then these are likely due to changes in the geometry. So this kind of measurement has been possible in this source, IRIAS 1322.4, which has been looked at with XMM over a very long time, 2 megaseconds. Of course, these measurements require very long exposures. And what has been observed is that the time delays get longer as the luminosity of the source increases, which has been interpreted as the height of the corona changing. Now, this is associated, this has been modeled using a very simple lamppost geometry. Of course, this might be an oversimplification, but in any case, what this is telling us is that the region where X-rays are dissipated change with luminosity and gets at larger distances as the luminosity increases. Now, another useful way we can use variability is to measure the black hole mass. So as you can infer from this plot already, there is a strong dependence of timescales on the black hole mass. So basically, the smaller the mass, the shorter the timescales. So this has been proved by measuring the position of this break in several Aegean and in extending it to black hole binaries. And what has been shown is that this break scales with the black hole mass following these relations. But it has also been shown that this break depends also on the mass accretion rate. So if we are able to see this break and measure it, we could infer the black hole mass, but there would be some uncertainty related to the mass accretion, to our knowledge on the mass accretion rate. And the other problem is that this break is not always easy to measure. We don't always see it in Aegean. We are always limited by this frequency window that I discussed before. However, as the break moves with the black hole mass, what also changes is the What also changes is the area below between two distinct given frequencies, the area below the curve that describes the power spectrum. Now, this integral here corresponds to the variance of the Lightcurve, so the excess variance. So what this is telling us is that the excess variance also depends on the black hole mass. And this has been proved by looking at a very large sample of sources. And what has been seen is that as the black hole mass increases, the excess variance decreases. And it does that with a very small scatter of the order of the uncertainty of reverberation mass estimates, reverberation mapping mass estimates. And why is that? Basically because it has been shown that there is a very, there is no relation with the mass of this parameter on the mass accretion rate. And so this is a much easier way to estimate the black hole mass. The reason is that basically it is possible that the normalization of the power spectrum at the break counterbalance any dependence on the mass accretion rate of the break itself. So this is an easy way to measure a black hole mass if you want to make a time-averaged spectral analysis of a source, but you need to know the mass to estimate some parameters. You just take the light curve, you measure the rapid variation, you measure the variance of the light curve, and then you can infer the black hole mass. Another way to constrain the black hole mass would be to measure, to detect orbital modulations in some spectral features. And the best way to do is to look at the iron K line. This has been done in several sources now using these so-called excess maps, where basically one looks at the excess emission over the continuum as a function of time and energy. And the goal is to look for patterns of modulation in both time and energy. So we can extract light curves over a range of energies. And in some cases, it has been shown that there is some hint of modulations. And this modulation, if due to orbital motion, would allow to constrain the black hole mass. Now, the problem with this is that usually the light curves are short, so we cannot follow the modulation over very long time scales. And as Alessandra discussed yesterday, stochastic noise is a bad beast. And this is, and basically what it can do is to produce fake modulations in the light curve. So the best way to deal with that would be, again, to have very long monitorings to prove, but also you should, oh, wow, okay. Okay, let's go faster. So another way, another important way to use variability is to look, we can use variability to study absorbers. Absorber would imprint important features in the variability of the source. This is, for example, the case of 3783, where we show the fractional variability, which is the fraction of variable flux in this source as a function of energy during an unobscure state and then one obscure state. As you see, there is a lot of change, and what we have found is that this excess here is due to changes in the obscurer. So this can produce other changes as well. For example, we can look at the coherence, which is the level of linear correlation between light curves, and when we have an obscurer in this source, we see a drop of coherence. So basically, this means that the light curves in this source are no more linearly correlated. Now, we can model all of that and infer a recombination time. And from the recombination time, it is possible to estimate the distance where this absorber is located. Then we can use variability as a tool to find Aegean in aid of other techniques, other spectroscopic or photometric techniques. In this case, it is very important to take into account the survey strategy, because this measurement, so our sensitivity to detecting Aegean depends on the length of the survey. Basically, the longer the length, the higher the fraction of variable sources. This is because of this red noise shape of the power spectrum that I commented on before, because these sources are more variable on longer time scales. And then it also depends on the cadence of our observation, because this reduces the errors on our measurements of the variance. Now, this is to show that also the wavebands matters, but if we look at X-ray bands, we see basically no difference between the fraction of detected type 1 and type 2 Aegean. Now, very quickly, let's go through transient phenomena. This is not really my field of expertise, but I found it very interesting to mention these topics. So we know about three kind of transient phenomena in Aegean. So the first one is tidal disruption events. So these events occur when a star is ripped apart by a supermassive black hole, and basically a fraction of the star is accreted, producing a flare of electromagnetic emission. Another fraction is put on an unbound orbit. And because of this accretion process, it is possible to observe this sudden increase of luminosity from these sources. And now, these sources are usually quiescent, so these Aegean are usually quiescent. So what basically is observed is this sharp increase and then a slow decrease that takes years to occur. And basically, this is a very characteristic light curve that allows us to find tidal disruption events. Now, so this is a powerful way to find quiescent supermassive black holes. It doesn't mean that these events do not occur in Aegean, in active Aegean, but in this case, it would be much more difficult to disentangle this trend on top of the long-term variability. Now, since yesterday we talked about dual binary black holes, this is, okay. So we can go. I have only 2 more slides. Okay, let's go on like this. No problem. So this is an interesting result because on top of this TDE, what has been found is these 2 drops that occurred. So the source disappeared basically 2 times during this decreasing curve. And basically this has been interpreted as due, fits very well with a model where the system is formed of 2 supermassive black holes, and the secondary black hole is perturbing the accretion flow, so is basically interrupting accretion over these periods. And this, of course, will be a very good source of a gravitational wave in the future. And then for transient phenomena, we have changing look Aegean. Changing look Aegean are Aegean that change types from type 1 or type 2 or vice versa, and they can do it several times over their life. And genuine changing look Aegean are those where they cannot be explained by obscurations. Now, the point is that these changes occur on relatively short time scales. And one interesting result has been found in this source, where basically when this changing look Aegean is brighter, what changes spectrally is the emergence of a soft excess that is best fitted with a warm comptonization component. So this is thought to drive the disappearance of broad lines. Now, to explain this, a distinct instability models that is used for black hole binaries, that is usually used to explain state transition in black hole binaries, has been proposed, but the timescales in this case are too short. Okay, let's go on. So the last and newest example of transient phenomena are QPs. Now, I don't have much to say about QPs simply because they are new events. We are starting to characterize these events, but what has been proposed is that they might be the electromagnetic signatures of extreme mass ratios in spires, again involving the presence of binary black holes. Okay, so I will leave you with takeaways and we can discuss this.
Okay. The speaker, thank you for the nice talk. And other questions? Time for a couple of questions. Yeah.
Thank you. Very nice talk. Can you talk about a bit more about QPE?
Okay. Thank you. Okay, so these are soft X-ray eruptions in the sense that basically we see them only in the soft band. And they repeat quasi-periodically, and they show these peaks of emission that repeat. So basically what has been observed in this source is that there is one large amplitude peaks followed by a smaller amplitude one, and this pattern repeats. And basically, QPEs have been detected in 4 sources so far, 2 with the Rosita, and there is 1 candidate. And it seems there are 2 distinct populations of QPE so far. So one showing this regular pattern, the other one showing peaks that are a bit messed up. But this has been recently modeled with a superposition of different QPEs. And basically, these also show a spectral evolution. What is observed is basically a transition between one thermal thermal component dominated spectrum to two thermal components dominated spectrum, but this second configuration is associated with the presence of is better fitted with a like Comptonization component. So a warm Comptonization component plus a disk black body. Yes, and so like as for the theoretical interpretations, basically it seems they fit better with a model where we have a supermassive black hole plus at least one stellar mass black hole. And basically what the stellar mass black hole is doing is that when it orbits the supermassive black hole, hitting the disk, it produces these flares.
Okay, time for one more quick question. No more questions. So we thank the speaker again. And we welcome the next speaker with Dragana Ilic.
Good morning, everyone. It's very nice to be here. I want to thank the organizers for giving me the opportunity to talk about the exciting variability in the optical band. Even though I'm totally in the group of X-ray variability talks, I think optical variability is very exciting, and especially it's going to be super exciting with the coming LSST. So I am a spectroscopy person by background, and for the last 20 years I've been doing spectroscopy, and this is my first talk where I'm not going to show not a single spectrum. But still, I think spectroscopy is the most powerful technique, but waiting for effective large spectroscopic surveys, let's see what we can do with LSST. And this is Thank you. I am from the University of Belgrade and currently based at University of Hamburg as a Humboldt Fellow. So I want to convince you that the LSST is coming, and LSST is super powerful. And this is the work that has been done with a large group of people listed here. Oh, yes. And within the project that we have been awarded by the LSST Corporation within the last year, and it's about building deep learning engines for Aegean light curves. And basically, this was the funds to support 2 students. Yeah. I'm doing a mistake with which everyone's are doing, yes. So these 2 students, Isidora Yankov and Eva Čvorović-Hajdinak, and I want to say hi to them because I know that they are listening over YouTube, and thank you very much for doing the huge work. And you can follow us on these two websites, and I also want to thank all my collaborators. So why we want to do this, and I just want to spend some time in presenting the LSST. You probably all know about that, but just few words. This is going to be a digital movie, color movie of the universe with basically 10-year-long color movie, which will give huge opportunities to study the optical variability of many objects, but also especially Aegeans, which we know that are one of the primary variable sources in the universe. And in one word, the LSST is the optical near-infrared survey of half of the sky in these bands. It will reach up to around 27 magnitude in our band over 10-year period by co-adding basically images, around 1,000 visits. And the main survey is the wide, fast, deep survey, and here you can see the operation simulation of the number of visits of different portions of the sky, and these yellow dots are basically the deep drilling fields, which will especially be focused on Aegean science, and it will produce billions of galaxies and stars, and most importantly, it's the time domain astronomy in one word. And to illustrate the power of LSST, this is the SDSS image of 3.5 square image, arc-minute square image of the sky, and this is what the LSST will see. I mean, I can like go for the whole day looking at this. It's going to open the totally new parameter space in the optical sky. And this is just a tiny area. LSST will deliver 5 million of such images. And when it comes to Aegean, the rates of discovery is that it will be about 10 million quasars. We hope that we will be able to go very deep as well. About several thousands of quasars will be detected at very high redshift. And as I said, there will be 5 deep drilling fields, which will coincide with other very important missions. Like just recently, another deep field has been added to coincide with the Euclid deep drilling fields. So a lot of, as well, Chandra and XMM, so a lot of potentials to joint efforts of the basically other surveys. And when it comes to the Aegean variability, there will be millions of light curves ready for us to explore. And so the point is, how can we tackle this? And this was one of the aim of our research, basically, how can we build some tools to work with this huge amount of Aegean light curves? And to tell you that the LSST is really there, it is there. The first light is you know, it's like now it's fixed in stone that it will be next April 23. And we are currently basically somewhere here defining the final operation strategies for the LSST. And the commission is starting next year in April. And the full operation should be basically end of 23 when the survey is going to start. So just to follow up a little bit, why optical light curves? I mean, as well, we are now here in completely different timescales when it compares to the X-ray. So these are more like days, weeks, sometimes even months, depending on the luminosity. And we can do a lot of exciting science. And I want to thank Elena Del Bonte and Thomas Trieu yesterday for very nice talks about the reverberation mapping in the optical bands. So we can, and they stress the need to constrain better the radius-luminosity relation, which has been widely used to estimate and also the mass-luminosity relation. And that's one of our aim is to basically see how can we do reverberation mapping with the photometric data. And another large part which our group is working, which I'm not going to tackle at all here, is the hunt for the periodic system in the optical light curves. And basically, we have been working a lot on this, both from developing the tools to detect reliable periodic system, as well to model the optical signal in the periodic system. And we have, I think you know by now that light curves of Aegean are super problematic. You know that they are basically immersed in red noise, and this is on all in all bands and the optical band as well, and this has been shown for a large number of SDSS data, and they are of course stochastic, nonlinear, but this is from the sort of physical point of view, but from the technical point of view, they are a complete mess. So you have irregular sampling, you have gaps, it's a mess. I mean, if you want to extract the reliable information, you have to think of a tool how to address these light curves and basically do some preferentially non-parametric modeling of light curves. And these were two main goals of our project of deep learning engine, is to see how can we basically use machine learning tools to model our light curves, and then employ these light curves for the photometric reverberation mapping. So you probably have heard about this is the red noise. So basically described by the sort of the power spectrum is describing the random, basically the randomness. So it's the most important and well-known model is the damped random walk model to model basically the light curves. And there has been recently some attempt to use machine learning approaches. Here we use the conditional neural processes, which are basically non-parametric modeling for Aegean light curves, and it's a sort of a supervised machine learning technique. And you see here a very nice by basically putting some contextual points, we are reaching the target point and able to reproduce the light curves with a very irregular shape. And this had been just recently accepted and published in this paper by our student Eva. And we tested this. The first tests were done in this paper for on 150 light curves from the Assassin survey. Basically, we selected wanted to have light curves of a various type and shape with strong gradients, like here, with gaps and many, difficult features to model with the non-parametric models, but also with the Gaussian processes or any other tool. And we were super surprised and very happy to see how this conditional network processes were basically quite good tool to model these stochastic processes. And we are now testing this on a large number of ZTF light curves, the Zwicky transient facility light curves, which are giving thousands of light curves, and we are trying basically to see how can we tackle a large amount of data in preparation for the LSST. The second part of this project was focused on the tools to test and develop more the photometric reverberation mapping, and this is a formalism developed by the Shelush and Daniel, a very nice way. How can you basically extract the information from the photometric light curves, because we see here, so this is, I have one spectrum. This is one spectrum overplot on the SDSS wideband, broadband filters, and you see that the line is basically immersed in this broadband flux. So you basically have to disentangle the continuum flux from the line flux by combining different filters. And Shelush and Daniel, in a series of papers, there is also an Edri et al. Paper, very nice papers, show that basically by combining the cross-correlation function of two different bands, for example, let's say R and I band, and the autocorrelation function, and by measuring this tiny difference here, you could actually extract the time lag. And they show this very nicely. Thank you very much, Paula. We did the test by modeling the light curves using the damp random walk described in our 21 paper, and tested it on different cadences. We wanted to test this on the LSST cadences, which were released by the operation simulations. And here you can see, because these are model light curves, we know what is the true lag, the time lag, and you can see that for different cadence strategies, we were able to extract the light curves. And this tool is being more developed, and our aim is basically to make it available at the Astro Data Lab, and you can, it was shown on this very nice workshop that we did this year for both students from Ethiopia and Serbia. And you can go here and have a very detailed notebook and go through, and it's a very nice notebook. I don't have time to click here. And what we are very happy is that we are going to produce a Python version of ZDCF cross-correlation analysis tool, which is useful for these sparse and gappy light curves, and can be, of course, applied on any light curve. And I want to thank basically the people from the Weizmann Institute in Israel for providing us, basically allowing us to do this update. So my summary is that LSST is coming. It's going to be super important. We need for measuring basically for Aegean accretion disk structure, as well as the broadline region radius, as well as to hunt for the periodicities in light curves. But we need basically machine learning tools in order to tackle all the problems. And finally, I just want to say that you can all should involve in LSST somehow, or at least follow what's happening. There's a lot of way how to follow what's there. And one very active science collaboration, which I've been a part of for the last 2 years, is the Aegean science collaboration. And one interesting thing to address is this data challenge that they released last year. But the data sets are still available for you to learn what would be the data products of the LSST. And it's this website, and I just want to point you for the poster of Vincenzo, who basically was one of the contributors to the data challenge. And so see his poster.
Thank you. Thank you for this nice talk. Time for a couple of questions.
I was speaking too fast. This is the 12-minute stuff. But it's good.
Hi, thank you. It's for the very interesting talk. Curiosity. So these machine learning tools are taken as standard tools, I mean, as baseline tools for the distribution of and analysis of the data for LSST, or it's something on top of what is more standard and tools for production of data, Lightcurves, etc.
The basic formalism is already there, and it's the same basically thing whoever was doing with machine learning applications. There are many formalisms already developed, but the point is that you need to design your own, structure and your architecture for your own problem, and this is something which is custom-based. So you have to, I didn't have time to go into details for this, but we explain it in very details by putting all the diagrams and scheme in the paper. So you should check the paper, which I'm not listing here, but yeah.
Okay, time for another quick question, if there is any. No more questions, so we thank one more question. Yeah.
Thanks for a nice presentation. I was curious if your machine learning method are already giving any result on ZTF and archival light curve. So is there any pattern that is coming out?
Yeah, thank you very much for this question. And this is, so we are basically, expanding our network in terms of wanting it to be unsupervised learning of a large data set. You need the large data sets in order to build and apply unsupervised learning. And so far, we were super happy with the preliminary results. So this is super preliminary. By making the network to learn on the ZTF data, it was able to basically predict the behavior of the light curves, which was quite exciting for us. And it is super slow. That's one of the biggest challenges. But right now we are very happy that we got access to some supercomputer in data center in Serbia, or based on GPUs. So we are testing it now on GPU. So we'll see how it goes, but it's very promising so far. Thank you.
Well, we thank the speaker again, and we welcome the next speaker, who is Fabio Vito, and will talk about remarkable variability of a quasar at cosmic dawn.
Okay, thank you. So I'm going to talk about a very strongly variable quasar, redshift 6. Just to put this into context, all the quasars we know at high redshift 6 and higher are very massive, 10 to the 9, 10 to the 10 solar masses. So they are put somewhere here in this plane, black hole mass versus redshift. And if you want to trace back their accretion, and meet the initial masses predicted by models of black hole formation, we had to account for continuous Eddington limited accretion. Several multi-wavelength observational programs have been ongoing to study the observational properties of redshift quasars, and one of the most important results is actually that the observable properties of redshift quasars are very similar to low redshift quasars. For instance, in X-rays, we see that the population of high redshift quasars that we observe have very similar luminosities as a function of volumetric luminosity as what we found for low-redshift quasars, and also we studied the alpha X versus UV luminosities. Basically, they behave exactly like low-redshift quasars. I'm going to focus in particular on one quasar at high redshift, redshift of 6. This is J1641. It was found to be extremely bright in 2018 with Chandra, with an observation with Chandra, and indeed was an outlier, a positive outlier of these relations. And from the magnesium to emission line, actually a black hole mass was estimated to be of the order of 10 to the 8 solar masses. So this quasar is actually creating a super radiant rate. So this was the Chandra observation in 2018, where the quasar showed very bright X-ray emission. This is a field source, completely unrelated source. So we decided to follow it up with XMM last year because we wanted to get, for instance, a spectrum of this quasar. And we expected something like hundreds of counts, hundreds of photons. But actually what we found is that the quasar disappeared. You still see the field source, which is pretty bright, but we don't see the quasar anymore. So we could put an upper limit to its luminosity in 2021 to be about 5 times 10 to the 44 X per second, which is to be compared with the luminosity 3 years ago, which was 3 times 10 to the 45 X per second, which means that this quasar varied by more than a factor of 7 in a very short rest frame time. This is about 3 months in the rest frame of the quasar. And here I show you how the extreme luminosity varied as a function of volumetric luminosity by factor of 7 in this time step. So to be compared with, to compare the variability of this quasar with the general population of quasars, in this plot we have the fraction of quasars in log, which is a fraction of quasars which are variable by some factor, and the factor is here on the x-axis, and this is log 2, divided by the luminosity of the quasars and also by the time step between the epochs. So we have short, intermediate, and long separations between the epochs, which means about days, months, and years. So in this plot, J1641 is somewhere here, which means if we compare this position with these curves, we see that less than 1% of all quasars in the universe are as variable as J1641 at redshift of 6. Actually, this is not the only variable quasars we know at high redshift. There is at least another quasar, which is J1030 at redshift 6.3. This is the X-ray light curve of J1030, and in particular between the second and the third epochs, it varied by a factor of 3. So now we have 2 variable quasars at high redshift, and we don't expect many actually. So is X-ray variability somehow enhanced in high redshift quasars? And to kind of test this, I collected a sample of high redshift quasars with multiple X-ray observations, okay? And I computed the X-ray variability factor as a function of the rest frame time separation between the different epochs. So we have 10 quasars at a redshift higher than 6, and most of them are consistent with no variability at all. This is J1030, so it's variable by a factor of 3, and up here is J1641, and this is a lower limit. So again, it's a remarkable object. So we have 2 quasars at high redshift which are strongly variable out of 10 with multiple X-ray observations, which means a fraction of about 20%. To be compared with the general population of quasars in which we see something like 10%. So this kind of suggests that X-ray variability in high redshift quasars is somehow enhanced. Of course, this is based on a small sample of objects, so we want to populate more in this plot. For instance, we can use the Hyperion program which is led by Luca, which is observing high redshift quasars. Some of these quasars, with XMM, some of these quasars have actually previous X-ray observations, so we can put them in this plot and kind of compute better this fraction. And also would like to mention that we got a multi-cycle monitoring program with Chandra on this quasar, 3 years, so we will follow the X-ray light curve and we see if it continues to vary or not. So since the X-ray and UV emission quasars are somehow correlated, we might ask ourselves what happened to the UV emission of these quasars. Is it variable as well or not? So J1641 is covered by several optical infrared surveys which sample the rest frame UV emission. We also added an LBT observation last year, and this is the UV light curve. We see that actually the UV emission is variable, but it became brighter from 2003 to 2016, and then it stayed kind of constant. So we have an inverted trend, variability trend between the X-ray and UV luminosity. Of course, these are the X-ray observation, the time of the X-ray observation. So we are not sampling the same time. The observation in the two bands are not simultaneous, and this makes the interpretation very difficult. We got also the UV spectrum of this quasar, and it's a typical spectrum of a high-redshift quasar. There's nothing really strange, except for the fact that we detected several narrow absorption lines in the spectrum. These are zoom in into the spectral ranges where we see these absorption lines, which are marked with vertical lines. And in particular, several of these lines, which are in red, we could identify them with transitions due to the same foreground object, an absorption system, a redshift 5.67. So we think that there is like a galaxy in front of this quasar, a redshift 5.67. So what is the cause for this strange variability of this quasar, very strong variability and inverted between X-ray and UV? We can have several possible causes. We can have a change of the accretion rate. You change the accretion rate, you change the luminosity, so you see the variability. However, here the problem is that we see this inverted trend between X-ray and UV bands. One possible solution is, again, that the observations in these two bands are not simultaneous, so we are sampling different states of the quasar in the two bands. Another possible solution is that actually some models of accretion onto black holes predict that if you increase the accretion rate, so you go close to the initial limit or even above, you're actually suppressing the X-ray emission and you're enhancing the accretion disk emission. So the UV emission, in this case, you will see an inverted variability. However, usually these models predict also the formation of strong nuclear winds, and we don't see strong evidence for the presence of these winds in the spectrum. Another possible cause is that we can have a small-scale absorption, for instance, by a thick inner disk. If you increase, again, the accretion rate, your inner disk might be geometrically thick, and it might actually absorb the X-ray emission coming from the hot corona. So in this case, you will see the X-ray emission become weaker. And this would, but the problem here is that this model does not explain the very bright X-ray state in 2018. And here a possible solution is, again, the fact that UV and X-ray observation were not taken simultaneously. This quasar might be gravitationally lensed. This is the first high-redshift gravitationally lensed quasar we know, a redshift higher than 6 by finite Tidal. These are HST observations. If also J1641 was gravitationally lensed, it would mean that it is less luminous than what we think. And less luminous quasars are more variable, so this would explain the strong variability. In addition to that, we can also have microlensing due to the motion of stars in the lens galaxy. Microlensing has been found to sometimes boost the X-ray emission, the observed X-ray emission of quasars. This would explain the bright X-ray state in 2021. Here, the problem is that we need a lens galaxy, of course, and the possible solution is this absorption system. We see a redshift 5.67. It could be a galaxy that is lensing, that is the lens of the system. Finally, the last cause we can have is that actually the bright X-ray emission in 2018 was not due to the quasar itself, but to a foreground transient event, for instance, a TDE. In this case, we need a foreground galaxy in which we can have the TDE, and we need it to be a low redshift because we want the luminosity to be consistent with the TDE, so it cannot be this object here. We don't really have a solution here. Just to conclude, oops, okay, I can go. We would like to have additional follow-up observation, both in X-ray and UV, in order to follow the light curves in these two bands. And we would like to have the observations to be simultaneous. Otherwise, the interpretation is very difficult. We've already granted a 3 years monitoring program with Chandra on this object, and we actually observed again this object with LBT 1 month ago. So we would like to observe it again in the next years. And finally, we would like to have high-resolution imaging, for instance, with HST, in order to probe the gravitational lensing hypothesis. And I stop here. Thank you.
Thank you, speaker, for the talk. And time for 2 questions.
So I was wondering another possible solution, like, for example, large-scale absorption, maybe in the form of an outflow or some gas cloud around. Could you rule it out?
No, I mean, that's a possible solution, but actually, if you have an outflow, you would expect to see absorption features, for instance, in the UV spectrum. We don't see them. Of course, this depends on the line of sight, basically. Maybe we are not really intercepting the wind, so we would not see the broad absorption lines. But we don't see any evidence for outflows. But in principle, yes, it could be.
Okay, any other question? Well, if not, we are slightly over time. We thank the speaker again, and we welcome the next speaker, with Alfredo Luminari, who will talk about modeling of X-ray outflows.
Ciao a tutti. Hi everybody. I'm Alfredo Luminari. I'm Alfredo Luminari and I'm working at Rome in INAF, IAPS and Observatory. This work has been carried on with many people. Most of them are here in these days. You can find some names here, but there are many others. Here there is a brief outline, so I'll concentrate on time variable X-ray outflows. I will start introducing briefly ionized outflows, even though there have been many talks before me that analyzed this aspect in detail. Then I will present a brief state-of-the-art and possible future direction for spectroscopic analysis. And then I will introduce the main topic of my talk, which is time-evolving photoionization, with a novelly designed spectral and ionization code, which has been is being applied to variable Aegeans, and also briefly I will touch on gamma ray burst, because even though it's a totally different kind of class, it has come strong physical analogies to what we are interested into. So, okay, so to start here, there is a brief schematic and partial picture of how we believe outflows are disposed in the innermost accretion disk. So at the center you have the black hole, and at increasing distance you have ultra-fast outflows in the X-ray, broad absorption line in the UV, warm absorb and narrow absorption line in the highest distances. So in the UV, lines are mainly in the carbon 4, silicon 4, magnesium 2 and forbidden oxygen 3 line. And, no, aspetta, ecco. And Justina then after me will hold a talk mainly on this. So broad absorption line can have up to relativistic velocity, and they cover a distance scale up to 500 parsec, and they are usually imaged through carbon absorption trough. For the X-ray band, instead, we have hydrogen and helium-like ions of carbon, oxygen, and hydrogen, magnesium, and iron. So they usually fall into broad classes. The first one is warm absorber, which are relatively less ionized with ionization parameter between 10 to the minus 1 and 10 to the 3, and velocity up to 1,000 kilometers per second. And they span a range between 1 parsec and hundreds of parsec. Here you can see perhaps one of the most famous examples, which is the 900 kilosecond Chandra spectrum of NGC 3783. On the high energy end, instead, there are the so-called ultra-fast outflows, or UFOs, which are very highly ionized, up to 10 to the 5, and have a velocity which are up to 0.1, 0.3 the speed of light. Here you can see a couple of examples. Here there is PDS 456 in the paper by Emanuele. And the other one is another source we worked on last year with also Marco Laurenti that will talk this afternoon. Okay, so I don't have time to talk on this, but there are several hints or evidence or tentative conclusions regarding a connection between the UV and the X-ray band. And this reminds us that all this study must be panchromatic and take into account the full picture in order to develop a fully consistent accretion and ejection scenario. In particular, I will focus now on X-ray spectroscopy, and still after 20 years after the launch of XMM and Chandra, which enable relatively high resolution X-ray spectroscopy, there are several questions that still remain open. Here I regrouped three most important ones. So there are several uncertainties on the location of such outflows, on their density and the energetics. For what concerns the location, the radius of X-ray outflows is generally estimated using lower and upper limits, which are built through indirect arguments and assumptions which are not necessarily true, and they have not been proved with sufficient strength. So here, as a result, you can see a plot with the lower and upper limit for the radial location of ultra-fast outflows in a sample of a local galaxy, and you can see that there is a discrepancy of 2 orders of magnitudes. And this is a paper of 10 years ago, but the situation is basically unchanged. And also the covering factor of these winds, which identified the fraction of the solid angle covered by such wind, is basically unconstrained, because this requires detecting and correctly interpreting the emission, which is even more difficult than absorption. So it is usually assumed by looking at the recurrence of UFOs in broad samples of homogeneous classes of Aegean, local Aegean quasars, but it is basically unconstrained on a per source basis. Density is even worse, if possible, in the sense that the gas density is a degenerate parameter when the gas ionization is at equilibrium, since the physical status of the gas and its spectroscopic appearance is uniquely determined by the ionization parameter, which is defined as the ionizing luminosity, or also the number of ionizing photons, it's the same, divided by the product between the gas density and the radial location squared. And so this means there is a degeneracy between these two parameters. But this is no more true when the gas is not in photonization equilibrium, but instead is time evolving, and I will touch on this later on. As a consequence of the uncertainties on the radial location, on the covering factor and the density, also the energetic of such outflows is highly uncertain. So here you can see the lower and upper bound for the mass and energy outflow rate for the same sample, and still you find an order of 2 uncertainty on these values. It is clear that in order to clearly assess the role of X-ray outflows in the broad Aegean picture, it is necessary to eliminate all these uncertainties and to precisely understand what are the properties and the impact of such outflows on the surrounding galaxy. Current limitations are both due to current X-ray telescope limitations, but also basic photonization modeling. In particular, the current approach to interpret spectroscopic observations is to build spectral templates with general purpose photonization codes such as cloudy, X-star, specs, or things like this. These codes are physically very accurate. They take into account radiate transfer and many line transition and ionization equilibrium. However, these codes are built for a general physical setting, and they are not specialized on the extreme physics at play in such highly energetic source. And as a result, the simulated spectra rely on several assumptions for what concerns the geometry and the kinematics of the wind. In particular, the wind is modeled as a layer of gas at rest with thermally broadened features, which are then a posteriori blue shifted in the process of the fit to account for the wind velocity. And for what concerns the geometry, all these codes assume the gas to be in a spherically thin geometrical shell with the luminosity assumed as a point source at the center, which is reminiscent of X-ray stellar atmosphere, which surely is not true for such complex sources such as Aegeans. And moreover, also the outflow is assumed to be in thermodynamic and ionization equilibrium. In order to overcome all these limitations, there have been a number of lines of actions in the last 10-15 years. First one is to perform a post-processing of time equilibrium solution, and this allows to overcome some assumption on the geometry and the dynamics of the solutions. The other thing is a totally different approach to perform not an analytic but a Monte Carlo radial transfer, and this allows to basically directly model the gas with its velocity and geometry. And the last one is to perform a time-evolving photoionization, which follow the gas ionization as a function of time when the light curve is variable. And we saw with the talk of Barbara that mainly all the Aegeans are variable to a certain extent, so this is very important. And the interesting things in this field is that when the gas is not in equilibrium, its evolution cannot be described through the usually ionization parameter Xi. So here I list a number of codes which try to follow these lines of action. Obviously, each line tries to solve some of this problem, but leave other problems open. There will be Gabi Panseu after me that probably will talk a little about, talk about this queen a bit. So now I will concentrate on time-evolving photoionization for 3 reasons. As I was saying before, the time-evolving spectroscopic feature cannot be mimicked with equilibrium spectra, so they deserve a detailed code which is especially designed for this. Time-evolving is also almost the only hope to constrain the gas density and then to drastically cut all the uncertainties associated to the energetic of the wind and also to the location. And as such will be fundamental for CRISM, which will open up the door for extremely high-resolution spectroscopy. So here there is an example of the light curve of NGC 4051. You can see here the count rate over time. You can see it's highly variable. On the bottom panel, you can see in red squares the expected gas ionization based on such counts, and in black the observed gas ionization. So you can see that the gas is not able to respond to the luminosity variation, and so it is not in equilibrium with respect to the illuminating source. In fact, the equilibrium time scale can be estimated through this formula, and you can see that the time over which the gas reaches equilibrium with respect to the radiative field is inversely proportional to the density, and so this means that for low density, the equilibrium time is longer, so the equilibrium is not granted, while instead for high density, this time is smaller, so we are closer to the equilibrium limit. And this is, at the end, is what allows you to break the density location degeneracy and to probe the gas density. So here we are building, for this purpose, we are building a time-evolving photoionization device which perform gas ionization integration over time, and at the end also produces absorption spectra to be compared with observation. There are several ingredients. The first one is the ionic abundance variation over time, which is composed of many terms. The other one is the temperature evolution, which is the balance between heating by photoionization and cooling by gas emission of lines. And then you also have charge conservation. So in a snapshot here, there is the workflow of TEPID. So you start by specifying initial conditions. So for example, here you have a simplified for the moment light curve. Then you specify the gas density and the initial ionic abundances. Then you perform a time-evolving computation. So you follow the gas ionic abundance over time. And at the end, you build absorption spectrum as a function of time. So here you can see the outputs. The light curve is such that the light is at equilibrium value at the beginning. Then you have an high flux, and then you have a low flux, which is equal to the initial flux level. You can see here oxygen, and then here iron abundances. The solid line is for a very high density gas, which therefore is in equilibrium, and you can see that it instantaneously responds to the luminosity variation, and so this can be described also by equilibrium photoionization techniques. However, when you go to 10 to the 8, you have a delayed response, so the gas adjusts to the light curve, but not instantaneously, and instead when you have 10 to the 6, which is the worst case, the gas is so underdense that it is never in equilibrium, but always lags behind the light curve. Here you can see the resulting spectra. You can see that in orange you have the instantaneous case, so 10 to the 10, and in blue the low density case. At the beginning they are in equilibrium at 0 for initial condition hypothesis, so there is no dependence on the density. Then when you go to 2 and 8 kiloseconds, which are the midpoints of the rise and the fall of the light curve, you see that the 10 to the 10 gas is able to respond to the higher flux, so it's more ionized and its opacity drops, and you can see that there are weak absorption feature. Instead, the low density gas is practically not responding, and so the spectrum is almost constant. And then the situation goes back to normal up to 16 kiloseconds. So this simple experiment here shows the power of time-evolving photoionization, which quickly allows you to constrain the gas density and therefore to build a more comprehensive picture of ionized outflows. Here there is a brief spin-off that I don't have time to discuss, but in any case we are applying also this to GRB, which are totally different sources, but they are intrinsically variable. So we are fitting gamma ray burst afterglows observed by XMM with a time evolving code. And here you can see a comparison. No, sta qua. You can see a comparison between a cold absorption fit, a fit with our time evolving model, and a fit with a time equilibrium photonization absorber, which you can see is totally unable to describe this gas. And this is a further confirmation that the absorption feature imprinted by the time evolving medium are totally unique and cannot be mimicked in any way by Cloudy or X-star or any other time equilibrium photonization absorber. So I leave here with my conclusion, and thank you for the attention.
Thanks, the speaker. And time for a couple of questions.
Thanks, Alfredo. Maybe I missed it, but I didn't understand whether in the end you are applying this code to real Aegean observations and then you measure the actual values for the density.
Yeah, yes.
What are these values?
This is the, yes, we plan to publish the first paper on time evolving with basically this work at the end of June, and then we plan to apply to actual observations, yes. And there are many variable Aegeans in the archive which can be interpreted with this model, and obviously the opportunities will be even bigger with CRISM. But yes, the goal obviously is to use this to real data.
Quick question. Which range of densities can this code probe?
This, I mean, can be applied to any density. The physics which we are implementing, which is here, is accurate up to 10 to the 15 over cubic centimeters. On the high density end, and the low density everything. So we are using also to simulate with, for example, with gamma ray burst, which have a density of 0.1, just to have an idea. So it can apply to any density range. We are also build an intelligent algorithm to determine the time step and the resolution step in order to match the resolution and the computing time. So it can be run with a laptop normal power.
Well, if there are no more questions, we thank the speaker again. And, we welcome the last speaker of the session with Giustina Vietri, and we will talk about UV wind at cosmic noon.
Good morning, everybody. I'm Giustina Vietri, postdoc at the Observatory of Rome, and today I will talk about the discovery of a variable and powerful ultra-fast outflow discovered in the UV at cosmic noon. And this work was done in collaboration with Enrico Piconcelli, Toru Misawa, and many others which are here during these days. So from theory, we know that the Aegean feedback is likely a two-phase mechanism, and in particular we have radiative forces that accelerate out ultra-fast outflow that from nearby the Aegean, and it shocks against the interstellar medium and then accelerate out the swept-up gas, producing large-scale outflows. And we know that the kinetic power of such UFOs are proportional to the third power of the velocity. So this implies that large velocity implies large kinetic rates. And to be efficient, the Aegean feedback, we know that should be in terms of kinetic power of a few % of the bolometric luminosity. So Enrico already told yesterday talked about the WISH quasars, which are the most luminous quasars, and why it's important to study them. And in particular, they are shining at cosmic noon in redshift range from 1.5 up to 3.5, which is the peak of both star formation and quasar activity. And the WISH are a sample of 85 type 1 Aegean, and they are hyperluminous, as you can see here in this plot of bolometric luminosity as a function of redshift. Here are the WISH with the bolometric luminosity larger than 10 to the 47 arc per second. In gray, you can see the SDSS population from Shen 2011, and in blue and in green, the cosmos from the type 1 and type 2 Aegean in cosmos from Lusso 2011. So we studied the broad absorption line outflows in this sample. We found a larger fraction of BAL, about 24%, larger than the fraction discovered in the bulk of the population of SDSS from Gibson 2009. We also found that these outflows have a larger maximum velocity, as you can see here in these histograms. You can see the WISH quasars here in orange, and in blue the Gibson sample. And moreover, we also found a larger variable bandicity index, which is measurement of equivalent width. So we can say that the BAL outflows in high luminosity quasars are more and faster. And moreover, looking at the WISH sample, we discovered two ultrafast outflows in the UV. What does it mean, ultrafast? So in general, BAL, we can see BAL, blueward the carbon-4, blueward the silicon-4, and so on for different ions. In this case, which is the quasar J1538, we found that actually we observed BAL blueward the silicon-4 without any absorption for the carbon-4. This implied that actually these absorptions are not due to the silicon-4 ions, but are actually ultrafast ions from the carbon-4. And about the geometry and the acceleration mechanism, and also the impact of these outflows, actually it is Boolean constrained. So, oops. Basically, this is, let's say, a picture of this quasar, and which is at redshift 3.5, and by definition is hyperluminous, and have a black hole mass of 6 per 10 to the 9 solar mass, and accrete near Eddington. For this quasar, we found outflows at all scales. So, focusing on the Broadline region, looking at the carbon-4, we found a blue shift peak. As you can see here, at this angle, it should be the peak here. Instead, we found a blue shifted peak of 2,000 kilometers per second. This means that there are outflows in the Broadline region at parsec scale. And looking at the oxygen tree, which is forbidden, so is in the narrowline region, we found a blue shifted oxygen tree of around 1,000 kilometers per second. This means that at the narrowline region, we have also outflows. And then we move out to the CGM, where we found a blue shifted Lyman alpha, of about 4,000 kilometers per second, and probing so the outflows at the CGM scale around 30 kiloparsec. So for this quasar, we have multi-epoch observations. In particular, we have 2 SDSS public observation and proprietary data such as MUSE, MODS, and FOCUS. Here you can see the time variation between 2 consecutive observations, and here you can see the comparison between these spectra. So here in blue, you can see the first one, and in pink, the last one. As you can see, we have 3 different systems. So with different velocity, and these BAL are highly variable, as you can see, both in shape but also in strength. In fact, if you I hope you can appreciate the last observation, the BAL totally disappeared. So we are saying that these are UFOs because the outflows in terms of velocity is in the range of 0.13, 0.18 in unit of speed of light. So they are very fast in semi-relativistic velocity. So we studied their variability because it's a power tool to understand the properties of such outflows. So here you can see the balancity index as a function of the multi-epoch observation. As you can see, the throw R, A is in the red, and the variation of B and C throw here in blue and in green. As you can see, they vary in a different way. In particular, B and C throw vary similarly, and the A throw actually vary in a different way. This means that maybe the mechanisms responsible for such variability are different between different throw. But what are these mechanisms? So the dominant mechanism could be the change in ionization or the transverse motion of the gas across our line of sight. So we try to understand what are the primary causes of this variation, and in particular we compare the first two epochs, the SDSS, because they have the widest wavelength range in terms, and so we can also probe the BAL for different ions. So here you can see the A and B C throw for the carbon 4, the nitrogen 5, Lyman alpha, and silicon 4. So for the B and C throw, we can see that actually the variability is not so similar. In particular, we found that the silicon 4 is almost stable while the other ions are varying. For the A throw, instead, it seems that the variability shape is almost similar, and also the silicon 4 is varying. So what we can say is that it seems that, and considering this picture and the one before with the balancity index, we can say that for the A throw, the gas motion seems to be the favored scenario to explain the variability of the A throw. Instead, for the B and C throw, the main mechanism seems to be the change in ionization. So we can constrain the distance of such throw. In particular, we put upper limit on the for the A throw around 60 parsec, but also we have seen that during the two observations with the smallest variability time, the carbon 4 is also varied, but we do not have information about the other ions. So we just assumed the same variability mechanism, and we found that such UFOs are located at 0.6 parsec upper limit, and which means for this luminosity, the broad region size. And this is consistent with the theory which predicts that the location of the BAL outflows are cospatial or lying just beyond the broadline region. And instead, for the B and C throw, we found an upper limit for the radius of 2.7 kiloparsec. Oops, sorry. So we have the radius. We can estimate the kinetic power of such outflows because we want to understand what is the impact on the host galaxy. So for here you can see the B and C component and the A component. And here is the kinetic power as a function of volumetric luminosity. We collect also from literature X-ray UFOs here in green, ionized outflows, BAL is in blue and in orange. We found that for the B and C, we have a kinetic power of the order of 10 to the 46 erg per second. For the A component, of the order of 10 to the 44 erg per second. So this means that the kinetic power for these two outflows is in the range of 0.1, 10% of the volumetric luminosity, which means that, okay, these are just upper limit, but if we consider such radius and so such kinetic power, the radius is equal to this upper limit, we can say that actually these outflows could have an efficient feedback mechanism on the host galaxies. But as I said, these are upper limits, so we need to collect multi-epoch observation on time scales of days and months, and also we need high resolution spectra. So just to a brief recap, we have seen that such outflows could have an impact on the host galaxies. And these are also easy to observe, such outflows, since they require very cheap observation. Instead, X-ray UFOs at this redshift require more time-consuming observation and are also observed with different ions. And J1538 is a very unique system because it has a multi-component, highly variable, and also an hybrid scenario which can explain such variability. So give opportunity of understand what is the physics behind these outflows, and so the potential effect on the host galaxies. And this is my last slide, and such ultra-fast outflows are limited in number, and up to now the BL outflows are searched up to a velocity of 25,000 kilometers per second, and see the Biscletti talks for high redshift, very high redshift BL, and instead for the UFOs we can reach up to 60,000 kilometers per second. There is a first systematic study done by Rodriguez Hidalgo 2020 who found 0.6% of such UFOs, and in the Wish quasar instead we found a fraction of 7–10% of such wind, so it is very promising. And here I put another UFO of discovery in the Wish, for which we have 3 different observations. And as you can see here, in this case, also in this case, we have highly variable outflows, and also the centroid of such UFO, which is of the order of 0.16 in terms of speed of light, is also varying. So this means it could be that in this case we have also acceleration of such UFOs. So I conclude here, I want to stress that we need a monitoring campaign with high resolution instrument to put a more firmer conclusion of such winds. Thanks.
We thank the speaker. Any question? Always from the back of the room.
Hi, nice talk and nice results. I didn't understand how many of these are actually X-ray bright and or X-ray detected, and are there any hope to get X-ray spectra of these?
We have not done yet a study of correlation between X-ray and the presence of such UFOs, but we are going to, because now we have focusing on such a more, let's say, larger sample. So we are trying to understand if there is, and it should be a connection between the X-ray luminosity and the presence of such winds.
Okay, if there is no more question, I would have a short question. You have shown the two of the quasars, and you have identified several features A, B, and C. If you can go back to the slide, yes, I think that you derive a distance for A, B, and C that is widely different for the 3 components. How can you explain that, considering that you derive the distance for A, and that is the largest one, and it is located at the highest velocity?
Because the physical mechanism behind is different. I mean, with the gas motion scenario, and you have that the radius in general, the radius depends on the time variability, okay? For the gas motion scenario, we have a square root dependence. For the change in ionization, instead, you have the second power of the time variability. So these imply strongly different results in terms of radius.
Okay, we thank the speaker again. And now the session before coffee break is closed. We reconvene at 11 after coffee.
Galactic.